Okay, I want to remind you um, what are the what are the main components that we'll see every time that we'll talk about linear programming. Then every linear programming will always have the following components. It will always, the components of linear programming problem will always, uh, when I'll ask you for homework and I ask you to provide a linear programming problem that whose solution implies a solution to some other problems. I'll show you plenty of examples of it, but let's understand what is linear programming problem so far. The first component that you must have in it are what are the variables. Maybe it's only linear programming in one dimension and then it only has one variable, say x, maybe two variables, x and y, maybe three variables, x, y, and z, maybe n variables, and then you usually denote them as x1, x2, dot, 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 xd. D here stands for the dimension. So first component, always tell me what are the variables. Second component, tell me what are the cost function. There should be a single cost function. It needs to use maybe all. Yes. Thanks. Um, I wonder how long I would have continued before I would catch it. Okay. Apologies. So we start. What do I expect to find every time that I'm asking you to provide a linear programming problem? I expect you to give me the following components that without it is not a LP, not linear programming, or not LP problem, or just a P for short. The variables, maybe it's linear programming in one dimension and then the variable might be only x, nothing else. Maybe it's in two dimensions, so I have two variables, x and y. Three dimensions, probably x, y, and z, or any other three letters that you want to use. Doesn't need to be these ones. Maybe it's in the d dimension. Let's say for every, for in the d dimension, your variables will be denoted x1, x2, dot, 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 xd. For example, we talked about the diet problem. In the diet problem, obviously, I'll have, yes, now I can read. In the diet problem, if I switch to D type of foods, then I need to say how many units from food type 1, say avocado, do I consume daily, all the way up to the D types, this type of food. You must tell me what's the cost function that you want to work with. And the cost function, of course, needs to be linear. It can be 3 times x plus 5 times y minus z. That's a linear function. If I try to add y times z plus x squared, then this is not linear, and this, as a product of two other variables, are not linear. Linear means a variable times a constant. Variable times a constant. Only and sum and summation and subtraction of such variables, such expression. So this would be a possible cost function. In other cases, you find it quite convenient actually to pick only one of the variables, say just to minimize z. It doesn't make the problem one-dimensional if I just have to minimize z. It doesn't make it necessarily a single dimension problem. It still might be in 3 dimensions because I have 3 variables, x, y, and z, with interesting relationship between them. But the only thing that I care for the cost is only the z value itself. And now comes a list of constraints. Again, each one of them should be linear. For example, x is larger than 15, y negative. 7x minus z is larger or equal than 47. 9x plus y equals 90. Each one of them are variables, and we have n constraints. So the word n will uniquely be preserved to denote the number of constraints. So in this case, n equals 4. And if my variables are x, y, z, then this is an LP in 3D. If the variables that I use are only x, y, and z, then the problem lives in 3 dimensions and it has 4 constraints. And in terms of the algorithm will not care at all if you're adding more and more constraints, but the algorithm, it cares very little, but it will care more if you're adding more dimensions. It cares of dimensionality as usual. And a solution to the LP would be values of, say, of x, y, and z. Say, I'll direct the camera in a second. X equals 5, z equals 19, and y equals 32. I'm not going to use much small board, but when I want you to solve the solution, then if the linear programming has a solution, then the solution, if I add x, y, and z, should be what is the value of x, what is the value of y, what is the value of z, if these were the variables of the program. Of course, if the program is two-dimensional, then I don't need 3 values, 2 are enough, such that what makes it a solution? It should satisfy all the constraints. When I put x equal 5, it does not satisfy the first constraint, so obviously x equal 5 is not a solution. But x equal 55 will do. X is larger than 15, y is also not in the range, let's leave it. I need numbers that will satisfy all the constraints, and in addition, it brings the cost function to minimum. So when I'll ask you in the homework to provide solution to linear programming, that's what I want to see. What are the variables? What is the cost function? What are you trying to minimize or maximize it is? And what are the constraints that tells you where am I, what makes combinations of x, y, z legit or not legit, solution or not a solution. And as we saw earlier, possibly I don't have any solution, because if I look for a point which is above this line, to the left of this line and below this line, then we saw that there is no point that is in the intersection of everybody. Okay, the screenshot is very choppy. Yes. Screen share. I don't use